Hello and welcome to this realist simulation What's New presentation for our third release of 2022. First, let me introduce myself. My name is Charles Turcanose and I am the Assistant Product Manager responsible for Realist 3D Computational Fluid Dynamics suite, VECTIS. Over the next 30 minutes or so, I will give you an overview of some of the new and exciting features in this 22.3 release. I would like to give a brief update on our 3D CFD VECTIS suite, a detailed CFD and solid heat transfer tool for propulsion and thermal systems. Over this presentation, we will talk about the objectives and directions we are taking with VECTIS, as well as how these are mapped into the offering we deliver in this 22.3 release. We will then go through the key features of the 22.3 release and discuss how these answers the CA challenges our customers are facing. We will also highlight how they assist them in building better product, faster, and more cost efficiently. The aim of Realist 3D Fluids offering is to deliver expert 3D CFD capabilities for your engineering solutions. As a provider of expert 3D CFD, our team specializes on providing bespoke and tailored solutions, helping our customers addressing complex problems in combustion and thermal analysis. This is enabled by our state-of-the-art ICE modeling capability and efficient coupled thermal analysis solver. The design and development of our 3D CFD product is informed by the engineering expertise of our business embedded in software workflows. Finally, VECTIS is seamlessly integrated in the wider Realist ecosystem suite, including tools for system simulations, 1D fluids, and mechanical analysis. The 2022.3 release focuses on helping our customers address the challenges engine developers are facing, namely the drive to develop even more optimized powertrain with low or no emissions while reducing the cost of the development process. Thus, in this release, we focus on features that increase VECTIS predictive capability, but also on workflow and user experience items that allow our customers to save on their most valuable commodity, engineers' time. To this end, we have introduced new models aimed at the development of complex gasoline or hybrid fuels and green hydrogen combustion, as well as new flame speed tables for a range of gasoline blends. A new automation approach through Parametric Solutions and Python scripting allows our customers to build simple yet efficient workflows for complex analysis, while an accelerated processing of thermal analysis is also introduced. Additional improvements are also brought for our pre- and post-processing tools in R geometry and R viewer. Let us now dive into some of these features and consider what the simulation challenges are, what are the solutions we provide, and how our users can address these solutions. The first of these features is the CPV decoupled NOx modeling. The new technological avenues being currently explored for further reducing the engine emissions lead to the development of CNG and hydrogen engines. These engines are usually retrofitted from existing diesel power plants and as such feature a large compression ratio and tend to operate very near the NOx limits. To accurately and robustly capture the NOx onset and subsequent flame propagation in this type of configuration, a new NOx model is introduced in VECTIS 22.3 aimed at premixed and partially premixed applications relying on the tabulated detailed kinetics CPVG computational framework. The key change introduced here is that the new model relies on the transport of the auto-ignition probability instead of the progress variable, while still relying on the information stored in the CPV table generated from detailed kinetic mechanism. When the ignition probability locally reaches the NOx threshold, a new flame kernel is generated and flame propagation ensues. The image shown here presents the experimental pressure curve of a gaseous fuel direct injection engine operating at mild knocking condition as visible through the pressure oscillations near TDC. The pressure curve predicted by the new model is superimposed over the experimental data and captures very well the onset of knock as indicated by the maximum autoignition probability value reaching the knock threshold around the time at which the knock is experimentally detected. The subsequent 3D visualization here shows the isovolume of progress variable larger than 0.5, meaning the burnt gases, colored by temperature, along with a volume rendering of the autoignition probability. The volume rendering changes rapidly around the piston ball lip to reach the threshold, at which point knock occurs. This new functionality is simply enabled in the CPVG equation combustion panel in the GUI by selecting the autoignition model type as ignition probability. The next feature concerns the modeling of lean hydrogen flame speed. Lean premixed hydrogen flames are characterized by the so-called thermodiffusive instability, in which the flame, even in the absence of turbulence, will accelerate due to an imbalance between mass and heat diffusion. This instability is expected to be promoted at the conditions at which the engines are operating, and thus need to be accounted for if a robust, accurate, and predictive hydrogen combustion model is to be obtained. VECTIS 22.3 introduces a new state-of-the-art modeling approach combining both laminar and turbulent closure modifications to account for the effect of the thermodiffusive instability onto the hydrogen flame speed. The new modeling approach has been derived from direct numerical simulation results obtained in collaboration with Newcastle University and consists in a new flame speed table for hydrogen that is shipped with the installation and a modification of the Peters flame speed closure. The image presented here shows a map of a parameter measuring the stability of the flame at various pressure and equivalence ratio for a temperature of 750 Kelvin and 30% of EGR dilution. We can see a stable region for the negative value of the parameter and an unstable region where the parameter has a positive value. And we can also see that the strength of the thermodiffusive instability changes quite significantly depending on the thermochemical properties of the mixture. Next, we can see a comparison of the laminar flame speed predicted by VECTIS against the DNS results for a range of the instability parameter. This demonstrates a very good agreement between the DNS results and the correlation used in VECTIS. The resulting map of laminar flame speed modification shows that in the unstable region, this region, the flame is accelerated compared to the usual 1D flame measurement. And this acceleration is highly nonlinear depending on the thermochemical conditions. Next, we can see a comparison of the turbulent flame speed predicted by VECTIS on the y-axis and by the DNS on the x-axis over a large range of pressure, temperature, and equivalence ratio conditions denoted by A to F, for which a sweep in turbulence intensity was computed. Again, an excellent agreement between VECTIS model and the DNS is obtained. Finally, the pressure traces obtained on an hydrogen-fueled single-cylinder research engine at Ricardo and computed with VECTIS are shown at two operating points with different charge lambdas. Both the legacy and the new modeling approaches are calibrated on the case with lambda equal 3, and when computing cases at varying lambda, in this case 2.5, the new approach is found to be much more predictive and accurate than the legacy approach. This highlights the key strength of the new approach in capturing the changing influence of the instability across a range of conditions by allowing a much more robust and accurate prediction. This new model is enabled in the GUI by enabling the thermodiffusive instability correction in the turbulent flame speed model panel and using the new hydrogen flame speed table provided with the installation. Moving on to the parametric solutions. This constitutes a new powerful feature for automation and productivity. It allows users to define parameters and case sets in the GUI and easily create different simulation configurations from a single GUI session. This enables applications such as design of experiment, model calibration, parametric studies, and much more. Furthermore, parameters can also be used to reduce the possibility of user errors by representing values such as boundary turbulence levels, for example, which should be the same in various parts of the model. Once the session has been parameterized, multiple simulations can be delivered through the case table, where each case represents a set of parameter values defining a particular simulation. In this video, we see how a new parameter, which defines the temperature of the rotor, is introduced into the simulation. We then show how we define 6 different cases with different rotor temperature in just a few clicks. The simulation accepts parameters for scalars, such as temperature, which we've just seen, but also vector components, profiles, boundary condition files, and motion files. Each parameter can be given by a static value, but also by an expression which is evaluated on the fly. This brand new functionality is described in VECTIS manual, in the new example called Parametric Study, and also in some of our tutorials where the use of parameters was appropriate. Embedding of CA tasks in complex simulation workflows, be it geometry design, optimization, or design of experiment modeling studies, can be accelerated significantly by automated scripted solutions. In this release, we built on the strength of Parametric Solutions and coupled it with the new Python scripting functionality to help engineers save time and build automated workflows using VECTIS. The workflow automation follows this sequence. First, parameters are defined in the session to cover the areas of interest. Then, a simple Python driver can be created to modify these parameters, which are then solved with simulations executed. The example shown here illustrates a throttle where we parameterize the angle of the throttle and the mass flow rate and use the new rotation moving boundary option to generate the simulations at different throttle positions from a scripted workflow. Now coming to the new feature of our pre-processing tool, RGeometry. Geometry contracting printing drastically reduces the geometry preparation and mesh assembly time for complex conjugated heat transfer analysis. Complex solid fluid assemblies typically include clearances and small gaps, which should be removed for CAE analysis. If left in places, such small gaps can make the simulation of heat transfer inaccurate or lead to a deterioration of the solver convergence and therefore of an increase of the computational time. This new RGeometry tool provides users with an option to easily fill and close such gaps and paint faces in contact, enabling fast creation of high-quality CHT meshes. Another useful application of this functionality is to automatically detect and paint surfaces which are in contact. Both operations are achievable manually, but it is often time-consuming and very demanding on users' attention. By replacing this manual process with our new tools, we have achieved a significant time saving in model pre-processing. The new tools are the contact filler, which inflates the selected body until it reaches some counterpart and hence closes the clearance. The user can choose which of the body will be modified and which remains unchanged. The user can also specify the maximum tolerance by which the body can inflate to avoid excessive deformation. The second tool is called Paint Faces in Contact and automatically creates new boundaries on both bodies which are in contact. Both new tools are directly accessible from the toolbar and are fully described in the art geometry manual. The 22.3 version of the post-processing tool RViewer introduces a powerful analysis functionality based on ISO volumes. This feature not only helps users create advanced visualization of the flow field, but also enables more complex and specific post-processing by selecting only a subset of the domain cells based on an ISO volume. Each ISO volume may be defined by the volume for which the variable of interest has a value greater than or lower than a given threshold, or values in between an upper and lower threshold values. Once defined, this volume can be used for detailed flow analysis, for example, extracting averages, probability density functions, etc., from the selected region of interest, such as, for example, a region occupied by liquid in a multi-phase simulation, burn zone in combustion simulation, or high temperature areas in thermal analysis. An example of visualization obtained with this tool is shown here, with the ISO volume indicating the reacting layers of an hydrogen burning engine, colored by the local equivalence ratio, and various slices indicating the NOx mass fraction in the burn region. This feature is directly accessible in RViewer using the Add an ISO volume plot button. Other notable features in the area of automation modeling and hardware support in this release are designed to help our customers transfer and enhance their existing VECTIS workflows and take full advantage of the new solver technology. Phase 1 batch mode for background geometry generation allows users to transfer their scripted workflows to VECTIS vSolve easily. The volume condition modifier from Cloud File enables the initializations of part of the simulation domain for easy restart of VECTIS vSolve simulation from legacy VECTIS or Phase 5 results. The output to text data from sensors provides optional text output for easy incorporation of VECTIS simulation into existing scripted analysis and post-processing workflows. The new wall film modeling and post-processing options provide access to detailed analysis of driving mechanisms for wall film with specific aims at port-injected engines. The support of the new 21.6 Intel MPI enables our customers to run VECTIS on newer systems, in particular later Red Hat 8 versions. In this release, the post-processing of large-scale geometries such as battery packs has been accelerated by up to 7 times, improving user experience for complex CHT setup. And finally, a number of new and improved training materials allow users to take full advantage of the new features and adopt them in their workflows. And this drives me to the end of the talk, which highlights the most important features of previous releases in case you missed them. In the past few releases, we have brought a new combustion workflow aimed at robustly and accurately predicting the effects of fuel composition on the emissions of an engine by a coupling between our tabulated and on-the-fly detailed kinetic frameworks. This introduced new advances such as a new suit model, various significant speed improvements for the tabulated and on-the-fly detailed kinetics calculations, amongst others. This new approach aims at facilitating the adoption of new legislation requirements for classical combustion engines powered by drop-in or e-fuels. An additional feature was brought to improve the simulation of piston cooling by using the volume of fluid method to simulate the fluid and liquid motions in the piston gallery or under the crown. This can be coupled with Realis FIS or Realis Vulkan models to provide more accurate heat transfer predictions. Then, we get towards better usability by introducing a new tool, Art Geometry, aimed at replacing the previous preprocessing suite with Phase 1. This new tool supports the whole process from CAD import to mesh export. It is capable of generating high-quality watertight surface meshes and provides numerous tools, such as the one presented earlier, for CAD and mesh manipulation. This reduces even further the turnaround time between CAD and mesh, while still maintaining the grid quality. Finally, the variable calculator in RViewer brings an additional tool for complex post-processing of the solution by allowing users to compute user-defined expressions that may be scalars, vectors, etc., through a powerful C-like language. In summary, we are continuously trying to match the most pressing engine challenges to make VECTIS the world's best CFD toolchain for powertrains. Thank you for your attention.